All right, folks. Continuing on our study of techniques of integration. The next section we're going to look at is just trigonometric integrals. So great section, nothing but trig integrals. And this section is it's going to be setting us up for trigonometric substitution, which is the next section. Folks, you're going to see several general methods of attack. Again, it's not possible to show you how to do every single type of trigonometric integral, but you will see several general methods of attack. And as I just said, what we learn in this section, it will be very important in the next section, which is trigonometric substitution. And as you could probably imagine, being really, really good with identities and being able to manipulate identities is going to be an important skill for this section. So at this time, I'm going to list the main, not all, but the main identities that will be important in this section. So the first one, this is a Pythagorean identity, which you should know. Cosine squared x plus sine squared x equals 1. The second Pythagorean identity, 1 plus tangent squared x equals secant squared x. And then the third Pythagorean identity is 1 plus cotangent squared x equals cosecant squared x. And power reducing identities. Well, you've seen this. Sine squared x equals 1/2 quantity 1 minus cosine 2x. And cosine squared x equals 1/2 quantity 1 plus cosine 2x. So these identities, not all that will be used, but these are the main ones. So folks, when we're integrating powers of sine or cosine, so that is when you're integrating like a sine to the m power x dx or cosine to the m power x dx, where that m is just a positive integer, we are going to be using identities. And the next example will be our first example. Will illustrate what I mean by that. So in our first example, we're going to evaluate the integral sine cubed x dx. So you know the drill. Get this in your notes because I'm heading off to the chalkboard to work through it. All right, folks, in this section we're going to really look at nothing but trigonometric integrals. This section will set up the next section, which is called trigonometric substitution. So we got a lot of trig integrals to look at in this section. So here's the first one. Evaluate the integral sine cubed x dx. So I've already mentioned it, but let me write it down again. An identity that will be really important for this integral. These are basic identities that you should know. Is cosine squared x plus sine squared x equals 1. Because from that identity you get for free cosine squared x equals 1 minus sine squared x. You also get sine squared x equals 1 minus cosine squared x. So here, for this, when I see a sine cubed x, or if I saw a cosine cubed x, I'm just thinking I need to do something so I can get a sine or cosine involved in the integrand. And I'm thinking that because a u substitution should then take care of the integral. So here's what I'm seeing. A sine cubed x. Well, I can write sine cubed x as sine squared x times sine x. This sine squared x, I can replace it, thanks to that identity, with a 1 minus cosine squared x. And see, the benefit, as I just mentioned, of getting a cosine involved from the beginning, getting a cosine involved, is the basics of u substitution. We know here if we let u equal cosine x, du is a negative sine x dx. So when I substitute in here, I'm going to have a 1 minus u squared And then my sine x dx, well, that's a negative du. So let me put the negative sign out front of the integral. This is pretty easy to integrate. I mean, we know the antiderivative. The antiderivative of 1 is u. The antiderivative of u squared is 1/3 u cubed. And now I will resubstitute my u. I'm also going to distribute the negative at the same time to get a 1/3 cosine cubed x minus cosine x plus c. So that's a basic trigonometric integral, how to attack a trigonometric integral. So I'd like you to do one right now, practice. So in the exercises, I'd like you to do number 9. You know the drill. Pause the video. You do number 9. Once you've done number 9, restart the video and I'll be here at the board working through it. Okay, number 9, you were asked to evaluate the integral cosine cubed x dx. So again, I'm looking at this, I'm looking at the integrand, and I'm thinking, you know, if I could only get a sine x involved in there, a u substitution should be able to help me finish the problem. So the first thing I would start off with doing is I would rewrite the cosine cubed x as cosine squared times cosine, because now, thanks to the Pythagorean identity, I can replace cosine squared x with 1 minus sine squared x. And if I let u equal sine, we know this, if we let u equal sine x, du is cosine x dx. So when I substitute in, I just have a 1 minus u squared, that's du. Antiderivative is just u minus 1/3 u cubed. And I resubstitute, and I'd probably rewrite this. I like to go from largest exponent to smallest exponent. You know, that's just me. I get a negative 1/3 sine cubed x plus sine x plus c. So hopefully you got that for number 9. Let's head back to the slides and see what is next. All right, so did that example, and hopefully you were able to do number 9. So continuing on, that's another example. Here we're going to evaluate cosine to the 4th x dx. So here I go, heading back to the chalkboard to work through this example. All right, this example, we're going to evaluate the integral cosine to the 4th x dx. So in the first example, we had a single trig function. The exponent was odd. I asked you to do a homework problem that had a single trig function as the integrand, and the exponent was odd. Now we're looking at, well, what happens if you have in the integrand the single trig function and the exponent is even? And here's how you need to attack something like this. First, you know, I would rewrite this as cosine squared x times cosine squared x. Cosine to the 4th is cosine squared times cosine squared. When I have just that even exponent, I'm kind of thinking ahead that I'm going to have to try to get to a point where I can make use of the power reducing identities. So for here, the power reducing identity we will use, remember, is cosine squared x equals 1/2 1 plus cosine 2x. So I'm going to put a 1/2 quantity 1 plus cosine 2x in for this cosine squared x and for that cosine squared x. So let me write that step in here. And, okay, next. 1/2 times 1/2 is 1/4. That's constant. I'm going to rip it out front of the integral sign. Now I'm going to do the 1 plus cosine 2x times the 1 plus cosine 2x. I'm going to FOIL that out. So let's see, 1 times 1, well that's 1. Cosine 2x plus a cosine 2x, that gives me 2 of the cosine 2x's. And cosine 2x times cosine 2x gives me a cosine squared 2x. So just kind of looking at term-by-term integration, we're really making some serious progress here. We know the antiderivative of 1 is x. We know the antiderivative of 2 cosine 2x is just going to be sine 2x. Cosine squared 2x. Okay, now we have a little issue with this one. I need to make use of that power reducing identity again. Now here's what you have to really kind of focus on. Let me grab my red chalk here. This is cosine squared 2x. Your power reducing identity is for cosine squared x. So all you have to do is replace, in the power reducing identity, replace x with 2x. So you'd have a cosine squared, here, replace x with 2x. If you replace this x with 2x, you have to replace that x with a 2x. So cosine squared 2x is 1/2 quantity 1 plus cosine, while 2 times 2x is 4x. So you just have to take a little bit of care there. So let me do that substitution. Okay, we still have a 1, we still have the 2 cosine 2x, cosine squared 2x. Well, power reducing identity gives that to be 1/2 1 plus cosine 4x. And I'm gonna pull this right up here, give me a little bit more room. So I have a 1/4 see, 1 plus 2 cosine 2x plus, I'm just going to distribute the 1/2. So that gives me a 1/2 plus a 1/2 cosine 4x. I'll do one more little step. 1 plus 1/2. Well, 1 plus 1/2 is 3/2. So 3/2 plus 2 cosine 2x plus 1/2 cosine 4x. And now I go term by term, getting an antiderivative. The antiderivative of 3/2 is 3/2 x. The antiderivative of 2 cosine 2x, well, that's just sine 2x. The antiderivative of 1/2 cosine 4x. Well, the antiderivative just of cosine 4x would be a 1/4 sine 4x. So that 1/2 times 1/4 sine 4x gives me a 1/8 sine 4x. And you know what? I have just enough room to go one more step. Distribute the 1/4 to get a 3/8 x plus a 1/4 sine 2x plus a 1/32 sine 4x plus c. That was fun. So, power reducing identity. Used it twice. I mean, if you look at this problem we just did, from here to here it was just an algebra rewrite. Here to here, stepwise, we used power reducing identity. From here to here, well, we did arithmetic. We just multiplied and multiplied. Here we used the power reducing identity. From this step to this step, we just distributed the 1/2. From this step to this step, we just combined like terms. That's arithmetic. From this step to this step, that was calculus. So really only one step of calculus. Everything else was just using trig identities and a little bit of algebra. But that one wasn't too bad. Let's head back to the slides, see what is next. I have a feeling now we're going to start to see what happens when your integrand has maybe a mixture. It starts off with some sines and cosines. So let's head off and see if that's really what we're going to do next. All right, so hopefully you saw in that last example, we made use of the power reducing identities, and it wasn't too bad. So as I mentioned so far, we've seen how to attack trigonometric integrals that had a single trig function in the integrand. And we've seen how identities were used, and also how after using an identity, the old technique of use substitution, it came out and it was used. We're now going to look at integrating powers of sine and cosine where both are present in the integrand. So let me give you, like this, call this guidelines, integrating integrals of the form, integral sine mx cosine to the nx dx. I generally attack this, and the strategy I have, it depends on whether or not m or n is an odd number. So if m is odd, I'm going to rip off one factor of sine x and then rewrite the remaining even power of sine using an identity. That will allow me to get it in terms of cosine x. Then a u substitution of u equals cosine x is usually used. On the other hand, if n is odd, so the exponent for cosine, if it's odd, I will rip off one factor of cosine, rewrite the remaining even power of cosine using an identity, and to get it in terms of sine. And then a u substitution of u equals sine x is usually used. So these are the general guidelines. It's a general attack strategy. Let's look at an example. We're going to integrate sine cubed x cosine to the 4th x dx. So I'm, get this in your notes because I'm going to head off to the chalkboard to do it. And I'm sure, I'll be employing the strategy that we just looked at. But I think it's an easier strategy than what you see at first look. You just kind of think about what's going on here, and then the strategy will make sense. So let's head off to the chalkboard and let's do this example. Hi folks, this example we're going to integrate sine cubed x cosine to the 4th x dx. And I just given you some guidelines, and those guidelines are rock solid. They work. Tells you what to do, like if m is odd, n is even, stuff like that. Here's what's really happening, and those guidelines are fine. When I see an integral, and my integrand involves sine and cosine, and yeah, I have different exponents in there. What pops into my head immediately is this identity and what pops into my head is that the derivative of sine is cosine, and the derivative of cosine is negative sine. And guess what's popping into my head is those are weapons that will help me attack this integral. In other words, I see a sine cubed x, and I'm thinking, if I were to see just a sine squared in there, I could use this identity to get rid of that sine squared and get a cosine. And it just so happens that if I look at sine cubed as being sine squared, well, we know sine cubed is sine squared times sine. And this is looking like what it said in the guidelines that you just saw on the slide. You know, I've ripped off a factor of sine x and I'm saving it. What I'm saving it for is the inevitable u substitution. And that's why I wrote those derivatives over there. Because now I see exactly how this problem is going to go. I see how to knock it out from here. Sine squared. I can replace sine squared x with 1 minus cosine squared x. And when I replace sine squared x with 1 minus cosine squared x, I now see, well, if I let u equal cosine, du is negative sine x dx, or a negative du is sine x dx. And that was the whole point for saving that factor of sine. And that's why I mentioned, you know, these derivatives over here. So if I do that substitution, see, I'll have a 1 minus u squared, u to the fourth. This is negative du, so I put the negative sign out front. And you know what, I'm going to distribute, let me pull the problem right up here. I'm going to distribute that u to the fourth. To get u to the fourth minus u to the sixth. Now the antiderivative is a piece of cake. Using the power rule, you get a 1/5 u to the fifth minus 1/7 u to the seventh. And I'm going to do two steps, maybe three steps at once here. I'm going to distribute the negative and resubstitute at the same time. I'm also going to rewrite it so that my exponents go from large to small. So if I distribute, that'll give me a positive 1/7 u minus a 1/5, and there's my u plus c. Not too bad, folks. So I'd like you to do one here. The one I'd like you to do is number 15. So you know the drill. Pause the video. Go to the exercises. Do number 15. And after you've done 15, restart the video, and I'll be here at the chalkboard working through it. All right, in 15, we're asked to integrate sine cubed x, cosine squared x, dx. I've kind of left my weapons that I think might be helpful. I've left that written up on the board over there. So the first thing that pops into my head is I see a sine cubed x. So if I rewrite the sine cubed as sine squared times sine squared x times sine x, that's sine cubed. And then if I make use of the Pythagorean identity to rewrite the sine squared as 1 minus cosine squared, a basic u sub will now take care of the problem. U equals cosine x, du is a negative sine x dx. So I substitute in. I have a 1 minus u squared. Here's a u squared. And sine x dx is, well, that's negative du, so I'll put the negative out front. And this isn't too bad. Hopefully your next step was to distribute the u squared to get u squared minus u to the fourth. And let me pull it up here. Getting an antiderivative, should have had a 1/3 u cubed minus a 1/5 u to the fifth. And then resubstitute, and I distribute the negative and resubstitute. I do that at the same time, and then I like to write them, as I've said already, largest exponent to smallest exponent. So I would get a 1/5 u, that's cosine x, minus a 1/3 cosine cubed x, plus c. Folks, that's all there is to number 15. Hopefully you got it correct. Let's head back to the slides and see what is next. All right, hopefully you saw that doing that example, helped you and you were able to do number 15. And those problems aren't too bad at all. They're probably easier than what that general attack strategy made it, appear initially. Again, the key, it just comes down to just, thinking about what's going on and being able to use trig identities. So we're now gonna turn our attention to integrals that involve powers of tangent and secant, and our attack is going to be very similar to how we handled sine and cosine. Let me point out, in your book, there's a decent summary box on page 536. It's table 8.3. If you want to see a general strategy, I'm not going to put a general strategy in here, but if you wanted to see one, I'm telling you where you could find it in your book. I'm going to do an example, and I'm sure that when I'm doing the example, I will employ what is seen in table 8.3 if you want to cross-reference it while I'm doing this example. So the example I'm going to do is I'm going to evaluate the integral secant to the 5th x tangent cubed x dx. So, get this written in your notes because I'm heading off to the chalkboard to do it. All right, now we're going to start looking at some trig integrals that involve secants, tangents. This example, we're asked to evaluate secant to the 5th x tangent cubed x dx. So when I see secant, tangent, any of those things that are involved, in the integrand, I kind of instinctively write the following down, just like I did with the other ones that involve sine and cosine. I write down that Pythagorean identity, 1 plus tangent squared equals secant squared. I know the derivative. Of tangent. I know that's secant squared. And I know the derivative of secant is secant x tangent x. So those might be some weapons that I'll find useful in doing a secant tangent type situation. All right, now I told you that there was a box, in your book. It was a table that showed guidelines on how to attack these. And I said you could look at the box in your book and you could actually look at it while we're doing this example. And I'm sure I'm going to employ stuff that is mentioned in that box. I might say it a different way though. I don't know. When I see a secant to the 5th and a tangent cubed, the first thing that pops into my head is if I can turn one of those exponents into an even number, I might be able to take advantage of the Pythagorean identity. In fact, I'm thinking, if I could turn this into an even number, well, if I know 1 plus tangent squared is secant squared, I know tangent squared is equal to secant squared minus 1. And I also notice the following. If I rip a factor of secant out of secant to the 5th, I make that secant to the 4th. I rip a factor of tangent out of tangent cubed, so I make that tangent squared. So I'm ripping a factor of secant x out of here, a factor of tangent x out of here. Starting to see what my next step and the step after that, I'm starting to see how I can finish the problem. In other words, I know the derivative of secant is secant tangent. So if I make a u substitution for a secant in here, du will take care of the secant x tangent x dx. So all I have to do is turn the tangent squared using the Pythagorean identity, I just need to turn the tangent squared into secant squared x minus 1. So now when I do that u substitution, when I let u equal secant x, du is secant x tangent x dx. So when I substitute in, I have a u to the fourth. Here's u squared minus 1. And there's du. That's pretty friendly. I mean, I would distribute the u to the fourth to get a u to the sixth minus u to the fourth du. And then let me pull the problem up here. Get an antiderivative, so it's 1/7 u to the 7th minus 1/5 u to the 5th. Resubstitute. See, u is secant. And that's it. That's all there is to it. So I'd like you to practice this. Actually, I have two of them I'd like you to do here. I'd like you to do number 27 and number 35. So you know the drill. Pause the video, go to the exercises, do number 27, do number 35. After you've done them, restart the video. I'll be here at the board working through them. All right, number 27, you were asked to integrate tangent squared x dx. This is actually a very, very friendly problem. If you just use the Pythagorean identity and you rewrite tangent squared as secant squared x minus 1, the calculus is just one step. The antiderivative of secant squared. The antiderivative of secant squared is tangent. Antiderivative of, well, that's an x. So you just end up with tangent x minus x plus c. That's it. It only took one step. Okay, that one wasn't too bad. Let's see how number 35 is. So 35, you're integrating a tangent x secant cubed x dx. So I'm kind of thinking maybe I better look at that secant cubed x as being a secant squared times secant. So if I think of secant cubed as being secant squared times secant, don't forget the tangent. Oh, that actually is pretty friendly as well, because if you let u equal secant, we know the derivative of secant is secant x tangent x. Oh, we have it right here. So you substitute in, you just substitute, you have a u squared. There's du. This is very friendly. A 1/3 u cubed plus c. Resubstitute, 1/3 secant cubed x plus c. So 27 and 35 actually ended up being a couple of friendly ones to do. Hopefully you got them. Let's head back to the slides and see what is next. All right, that one wasn't too bad. And hopefully you're able to do 27 and 35. And you're starting to say, hey, you know, trigonometric integrals aren't that bad. So let's look at the following example. We're gonna integrate secant to the fourth of natural log theta, all that over theta, d theta. So again, you know the drill. Get this in your notes. I'm heading off to the chalkboard to work through it. All right, this example, we're asked to evaluate the integral of secant to the fourth natural log theta, all of that over theta, d theta. Well, this is a good one. And I think the natural starting point is a u substitution. To let u equal the natural log theta, because then you know du is 1 over theta d theta. So when you substitute in, that turns this into, oh, well, this isn't bad, secant to the 4th u du. All right, so now how do we attack secant to the 4th u du? Well, maybe I should rewrite secant to the 4th. Let me put this step in here. Of secant squared u times secant squared u. And I could turn one of those secant squared u's, I'll turn this one, into 1 plus tangent squared u. And that's using a Pythagorean identity. So let me rewrite this secant squared u as 1 plus tangent squared u. And hopefully you see why I want to do that. That if I make a substitution for tangent, I know the derivative of tangent is secant squared. So let me use the yellow chalk because I'm going to make another substitution since I've already used the variable u and I don't get confused with all the substitution that's taking place. I'm going to use a different variable here for my substitution. I'm going to use w. If I let w equal the tangent of u, then we know the derivative dw is secant squared u du. So when I substitute in here, I just have a 1 plus w squared, and then there's my dw. Let me pull it up here. So when I get an antiderivative, I'll get w plus 1/3 w cubed. Okay, I resubstitute my w, which is tangent u, so I put tangent u in for the w. And now I need to resubstitute for my u. My u is natural log theta. So I'd have tangent of natural log theta plus 1/3 tangent cubed of natural log theta plus c. And that was a pretty slick problem. Now I have one I want you to do in the homework, but you have to be very careful on this. You need to remember something. Let me give you the following warning before I tell you which one that I want you to do in the homework. It's nothing new. I mean, it's an old idea. It's something that we've always had in the back of our head. And that is the square root of x squared does not equal x. In general, the square root of x squared equals absolute value of x. Now think about how this is, why this is important to always kind of remember this. Let's just say, for example, you were asked to integrate from -1 to 1 the square root of x squared. If you forgot that and you did not remember that and you thought, well, the square root of x squared is just x, and you proceeded to say square root of x squared is x, which, by the way, is not correct, and you'd say, well, the antiderivative is 1/2 x squared, -1 to 1. You use fundamental theorem of calculus, and you get a 1/2 minus 1/2. You get an answer of 0, which isn't correct. Because if you look at the graph of square root of x squared, it would have a graph that looks something like that. Clearly, the area of that shaded region, the area of that shaded region is clearly, it's not 0. So you end up at the wrong spot if you say square root of x squared is x. Square root of x squared is absolute value of x. On the interval negative 1 to 1, you have some negative numbers to worry about. I mean, if I change this interval to go from 0 to 1, if this were a 0, this would be fine. It would be fine because on the interval 0 to 1, x is positive. So that's a little hint. It's a little warning for doing number 39. So now I want you to pause the video, do number 39, remember this warning, and I'll probably make use of symmetry, even functions, when I do number 39. There's another hint for you. So pause the video, do number 39. When you're done, restart the video. I'll be here at the board cranking through it. All right, number 39, you were asked to integrate from negative pi over 3 to pi over 3 the square root of secant squared theta minus 1 d theta. Hopefully you all saw a great way to start the problem is to make use of a Pythagorean identity. The secant squared theta minus 1 is tangent squared theta. Hopefully you said, oh boy, I have to be concerned here. The square root of tangent squared does not equal tangent on the interval negative pi over 3 to pi over 3. I mean, it would equal absolute value of tangent theta. I mean, if you think of the graph of tangent on the interval negative pi over 3 to pi over 3, well, here's a quick graph. I know there's a vertical asymptote at pi over 2, a vertical asymptote at negative pi over 2. So from negative pi over 3 to pi over 3, there are some negative values involved, which is why you can't say that this equals the integral negative pi over 3 to pi over 3 tangent theta d theta. That isn't correct. On that interval negative pi over 3 to pi over 3, the square root of tangent squared does not equal tangent theta. On the interval 0 to pi over 3, the square root of tangent squared does equal tangent theta, because it would just be positive results. On the interval 0 to pi over 3, on the interval 0 to pi over 3, tangent is positive, so we're going to get positive results. So I might want to think about integrating from 0 to pi over 3 and say on that interval 0 to pi over 3, the square root of tangent squared is tangent. Then I'd have to put a 2 out front. I'm making use of, some properties of integration. So now just to finish this off, it's not too bad now. You have 2, the antiderivative of tangent. Remember I told you I use, I told you this back in the first section of the chapter, that I use the formula negative natural log absolute value. We'll evaluate that from 0 to pi over 3. So pull it up here. So you'd have a negative 2. Let's see, negative 2, that's natural log. See, pi over 3 comes in for theta. Cosine of pi over 3, cosine of pi over 3 is 1/2. So that'd be the natural log of 1/2. That's a positive number. Okay, minus, now the 0 goes in, so that would be a negative 2, minus a negative. So that's plus 2 the natural log. Let's see, cosine of 0. 0 comes in here. Cosine of 0 is 1. I could simplify this just a little bit. The natural log of 1. Natural log of 1. That's 0. So 2 times 0 is 0. Whoops, I left off the 1/2, sorry. So we get negative 2, the natural log of 1/2. Negative 2 natural log of 1/2. You know what? I can go a little bit further with this, and I'm going to just review some properties of logarithms. This is kind of fun. I can simplify this down. There are many ways I could go about simplifying it down. I'm just going to show you one way. Negative 2, natural log of 1/2. There's an old property of logarithms that says I could rewrite that as the natural log of 1 minus the natural log of 2. Well, we know the natural log of 1 is 0. So this simplifies to just 2 natural log 2. I'm not going to go any further. Just wanted to do a little bit of simplifying. It was kind of fun. I used some properties of logarithms. There are other ways to go from here to here. I just showed you one way. So hopefully you paid attention to the warning. Been a while since we've had to worry about that. That was kind of sneaky. That's all there was to number 39. That's all there is to this video. So you can now do all the exercises that were assigned for the trigonometric integration, trigonometric integrals, section 8.3. These exercises are vitally important because being able to attack a trigonometric integral is so important in the next section when we do trigonometric substitution. So that's it. Go do the exercises. Thanks for watching.